Namaskar. Today we are going to deal with the topic water in reeling. The water used in silk reeling plays an important role. It is estimated to produce 1 kg of raw silk from charaka. The volume of water required is about 100 liters. In mechanized silk industry, approximately 850 to 1000 tons of water is used to manufacture 1 ton of raw silk. If the quality of water is poor, the impurities suspended in the water will adhere to the silk, thereby the color, the luster of the silk would be influenced. The water used for cocoon cooking should be colorless, odorless and transparent. The pH of the water should be between 6.8 to 8.4. Water characteristics like hardness, alkalinity, pH conductivity, etc. influence the quality and productivity of the raw silk reeled. Silk reeling industry requires considerable quantity of water, and the proportions of water required by different processes in silk reeling industry are: for cocoon cooking it is 6.8%, reeling 65.5%, re-reeling 0.8%, boiler 9%, others 17.8%. Presence of calcium and magnesium ions in the water is responsible for hardness of water. In other words, bicarbonates, chlorides and sulfates of calcium and magnesium when dissolved in water causes hardness. There are two types of hardness. They are temporary and permanent. Temporary hardness can be removed when the water is boiled, whereas permanent hardness can't be removed just by boiling. This type of water should be treated either with chemicals or by ion exchange method or by filtration method or by lime soda process, according to the levels of the presence of these characteristics, in order to bring the water to standard quality required for reeling. Standard concentration of different characteristics of water for better reeling performance along with raw silk is presented here. Standards of water quality for reeling are: for pH at room temperature, the range should be 6.6 to 7.6. pH at boiling should be 8.6. The range is 8.4 to 9.2. Acidity in ppm acceptable is 1 and range is 0 to 10. And alkalinity in ppm acceptable is 27 and the range is 15 to 80. Total hardness in ppm is 20 and the range should be 70 to 90. Electric conductivity should be 70 and the range should be 35 to 350. Types of water. All natural water sources contain minerals. The mineral constituents found in greatest abundance are bicarbonates, sulfates, calcium chlorides, magnesium and sodium. Carbon dioxide content may be greater than expected as a result of decomposition of organic matter too. 3 water resources are described here. They are well water, spring water, lake water and surface water or river water. Well water. This water is usually clear with a consistent composition. It may contain sodium bicarbonate, calcium bicarbonate and magnesium bicarbonate, iron and carbon dioxide. Lake water can be clear but may be colored and slightly acidic. High acidity combined with the presence of dissolved gases makes the source corrosive. Although lake water contains some calcium, magnesium, chlorides and sulfates, the concentrations of electrolytes is low. Surface water contains sulfates, chlorides, calcium bicarbonate and magnesium bicarbonate. The content of minerals and impurities is determined by the profile of the area from which the water originates, plus seasonal changes too. Water quality is affected by the amount of industrial effluent discharged into canals and rivers. Impurities in water are discussed under the following heads: turbidity and color, alkalinity, hardness, iron and manganese. Turbidity. Turbidity and color may be caused by large or small mineral and organic particles suspended in the water. Mineral particles may include clay, silt, calcium carbonate and silica. Organic particles may include fine vegetable waste, fats and microorganisms. Sedimentation in tanks or reservoirs is adequate to clear large particles, but filtration is needed for small or colloidal fragments. Filtration using sand or the use of coagulants followed by filtration may be indicated. The color in water signals the presence of dissolved or colloidally dispersed organic matter of known composition, augmented colloidal iron and manganese. Alkalinity. Raw water contains bicarbonates in amounts dependent on their origin. Often, water may contain small amounts of carbonate alkalates. The number of bicarbonate and carbonate ions present may be isolated by titration using phenolphthalein as an indicator and methyl orange as an indicator in the second stage. Hardness of water. Water hardness is caused by calcium and magnesium salts. Other contributing elements to hardness include metallic ions such as iron and strontium. Note if the metallic ions present, they will be found in minute quantities compared to salts. Hardness described as permanent and temporary, where permanent is caused by nitrates, chlorides and sulfates and bicarbonates, which may be boiled to precipitate into carbonates, and removing the hardness cause temporary. Hardness can be measured when a given amount of potassium palmitate or oolate solution is treated using given amount of water, concluding when a shaken liquid produces a permanent lather. More sophisticated methods are now available where a concentration of calcium and magnesium ions are quantified by titration with ethylene diamine tetraacetic acid. Hardness is expressed in degrees, but the actual units measured vary from country to country. 1 unit calcium carbonate ppm of United States is equivalent to 0.056 of degree hardness of Germany. Iron and manganese. Iron and manganese may be found in water depending on the source of the concentration. The 3 types of impurities are ferrous and manganese bicarbonates in well waters when high amounts of free carbon dioxide are present. Ferrous and manganese sulfates in rivers containing acid mine waste waters, or iron and manganese mixed with organic waste. Iron is present in some waters at the source, but corrosion in pipelines and storage vessels may taint water. If a given source is alkaline, iron in the form of ferrous bicarbonate may be removed by aeration when ferric hydroxide is precipitated and carbon dioxide released. Aeration also helps to raise the pH by reducing the content of the dissolved carbon dioxide. The equation may go like this: 4Fe HCO3 twice plus O2 plus 2H2O yields 4FeOH3 plus 8CO2. Manganese can be released in the same way, but to ensure rapid oxidation, a pH greater than 10 is required through the addition of lime or caustic soda. Methods of water softening. This part looks at industrial water treatment using lime soda process, base exchange and demineralization to remove all dissolved salts. Lime soda process, in this method, hydrated lime and sodium carbonate are added to precipitate calcium and magnesium ions as compounds of low solubility. For temporary hardness arising from the bicarbonate, the reactions are as follows. Calcium HCO3 twice plus calcium OH twice yields 2CaCO3 plus 2H2O. MgHCO3 twice plus 2CaOH twice yields 2CaCO3 plus MgOH twice plus 2H2O. Calcium carbonate has a much lower solubility than magnesium carbonate. When water containing bicarbonates of calcium and magnesium is treated, it is the calcium carbonate which is first deposited. For permanent hardness, the reaction is CaSO4 plus Na2CO3 yields CaCO3 plus Na2SO4. MgCl2 plus CaOH twice yields CaCl2 plus MgOH twice. The CaCl2 formed in the last reaction is removed as carbonate by the sodium carbonate. It may be noted that when temporary hardness is eliminated by this method, no salts remain but permanent hardness and equivalent quantity of sodium salts is left behind. Base or cation exchange. This process relies on the exchange of calcium and magnesium ions which occur when water is passed through a bed composed of complex aluminum silicates commonly known as rhyolites. If Z represents the silicates, the reaction may be represented as follows. Temporary hardness is explained in the following reaction. CaHCO3 twice plus Na2Z yields CaZ plus 2NaHCO3. MgHCO3 twice plus Na2Z yields MgZ plus 2NaHCO3. Whereas permanent hardness, we see that CaSO4 plus Na2Z yields CaZ plus Na2SO4. MgSO4 plus Na2Z yields MgZ plus Na2SO4. In contrast to the lime soda process, the exchange process replaces the calcium and magnesium ions by an equivalent of sodium even when the hardness is temporary. The anions present are unaffected. The bed is made from zeolite in granular form, sieved to a particle size around 1 to 2 mm in diameter. Its capacity is limited and will eventually be depleted. However, the process is reversible and employing a concentrated salt solution can regenerate the bed. CaZ plus 2 NaCl yields CaCl2 plus Na2Z. When the calcium and magnesium ions are removed as soluble chlorides, they are replaced by sodium. A cyclic procedure is created of softening, regeneration, water wash to remove excess salt and softening, etc. Between the softening and regeneration, it is sometimes desirable to backwash by passing the water upwards through the bed for a short time to remove any matter which has filtered out of the bed. Water from this process may have hardness value as low as 0.5 ppm. Demineralization. If two exchange processes are used, one for the anions and one for the cations, the content of mineral salts may be reduced to that present in distilled water. Removal of metal ions may be carried out with one of the sulfonated resins in the hydrogen form, so that water running out contains hydrogen instead of metal ions. CaCl2 plus H2R yields CaR plus 2HCl. CaHCO3 twice plus H2R yields CaR plus 2CO2 plus 2H2O. The resultant carbonic acid breaks down into water and carbon dioxide, which can be removed by aeration, but the mineral acids remain. Regeneration of the exchange process may be carried out by the use of hydrochloric acid. Ion exchange types and the quality of the water treated is given here according to K. Song and Y.W. Lee. Quality standard of water. It is essential to carefully select the quality of rilling water, as it impacts rilling efficiency, raw silk percentage of cocoons, and the raw silk quality. The data given in table 1 gives a standard for quality of rilling water, and table 2 shows the pH values and water hardness desirable for cocoon cooking water. Table 1. Standard quality of rilling water according to B.H. Kim 1983, where he discussed about the standard concentration and the range of concentration of different characteristics of the water that is required for rilling. Color and clearness, it should be totally clear. Then smell, you should not have no smell at all. Suspension and sediments, no suspensions and sediments allowed. pH of water, standard concentration should be 6.9 and the range should be 6.6 to 7.2. pH of water after being boiled, it is 8.3. The range of concentration is 7.9 to 8.6. Specific electroconductivity, micromole per cm is 100. Range of concentration is 40 to 300. Hardness in ppm is 2 and range of concentration is 0.5 to 4. M alkalinity in ppm, it is 30. Range of concentration is 20 to 40. Total acidity is 5 in ppm and 3 to 15 is the accepted range. Heavy metal ion should be under 0.1 ppm and the range of concentration should be 0 to 0.3. Residue after evaporation in ppm, it should be 85. The range of concentration should be 50 to 200. Table 2. pH values and a water hardness suitable for cocoon cooking. For dipping part, the pH should be 4.5 to 5.5 for good drillable cocoons, 4.5 to 5.5 for poor drillable cocoons too. Low temperature permeating part, the pH should be 5.5 to 6.5 for good drillable cocoons and 6 to 7 for poor drillable cocoons. Cooking adjusting part, the pH should be 5.5 to 6.5 for good drillable cocoons, 6.5 to 7.5 for poor drillable cocoons. Finishing part, the pH should be 6.5 to 7 for good drillable cocoons and 7 to 8 for poor drillable cocoons. Analysis of Reeling water. pH. A pH meter can measure the value of pH. Next, acidity. A 50 ml water sample is taken from an original water and 5 drops of phenolphthalein indicator added. Titrate with 50 N NaCO standard solution until the yellowish color of the sample water changes to purple. Then use the given formula to calculate the amount of acidity. A, total acidity, that is calcium carbonate. B, amount of 50 N NaOH solution consumed for titration in ml. And C, amount of sample water used. Phenolphthalein indicator consists of 0.15 gram phenolphthalein and 0.05 gram thymol blue dissolved in 100 ml of 50% ethanol. Alkalinity. A 50 ml of water sample is taken from the original water and 5 drops of methyl red indicator is added. Begin titration by using 50 N N2S44 standard solution. Titrate when the bluish color of the water sample changes to purple where the pH is 4.8. Then calculate using the same formula. A is equal to B into 1000 by C, where A is the M alkalinity, B amount of the 50 N H2S44 solution consumed for titration, and C is the amount of sample water. Methyl red indicator comprises of 0.02 gram methyl red and 0.1 gram bromocresol green dissolved in 100 ml of water. Water hardness. A 50 ml water sample is poured into a beaker. pH 10 is reached by adding 1 ml of buffer solution and a few drops of EBT indicator to the water sample, shaking it for a while, and then begin the titration by using the EDTA standard solution. Terminate when the reddish color of the water sample changes to bluish color, and calculate using the formula A equals B into 1000 by C, and A is multiplied with 0.056 to get the degree hardness, where A is the total hardness and B is the 50 N amount of H2S44 used for the titration, and C is the amount of the sample of water in ml. Buffer solution preparation. The total volume to be 1 liter by adding the distilled water after 67.5 grams of NH4Cl is dissolved into 570 ml of NH4OH. EBT indicator. The total volume to be 100 ml by adding the ethanol after mixing 9.5 grams of idiochrome black tea and 30 ml of triethanol amine. EDTA standard solution. 3.7225 grams of purified ethylene diamine tetraacetic acid disodium salt is dissolved into distilled water and until a total volume of 1 liter is achieved. Thank you.